Well, good afternoon, everybody. Welcome to the Gresham lecture. I'm Chris Budd, the Gresham Professor of Geometry. Now, I hope you've either all had lunch or are going to have lunch after my talk, because today we're going to be learning about the mathematics of food. And I hate to say I won't be talking about pie charts. I thank you for one of the audience for that joke. Anyway, so we're going to talk today about the role that maths plays in the production of food. So basically, if you think about it, nothing could really be more important to us than food or drink. Well, there's one other thing, but I won't talk about that today. We all eat, we all drink. Food and drink is one of the defining things that all animals do, and human animals especially. And if you look at all the industries in the world, food and drink combined is simply the largest industry in the world. There is nothing more important to the human economy than food and drink. And therefore, it's a perfectly sensible and serious thing to talk about. And of course, if you get food and drink wrong, we all starve and die, and therefore that's a bit of a shame. So that's why I think it's very important for, quotes, serious mathematicians like maybe me to think about issues to do with food. Let's look at some statistics. The government recently, well, in 2012, published a list of what they call the 8 great technologies, and in a sort of loose sort of sense, I'm working my way through that list for these Gresham lectures, and on their list of 8 great technologies which are forging the future and they want to invest in, number 6 was agricultural science. Just to keep the sequence, my next Gresham lecture, number 7, will be on number 7, which is materials, and the one after that will be on number 8, which is energy. So the government recognises that agricultural science, food production, is hugely important and worth investing scientific money into. Here's a rough estimate. The food industry is worth about £100 billion per year to the UK economy. We don't make as many cars as we used to, but we make an awful number of biscuits. Okay, and if those biscuits are cracked, no one will buy them, and therefore we're losing money. So the food industry is worth a lot. The drink industry alone is worth £18 billion. And here's a nice statistic. 5 billion pints of beer are drunk every year, which works out quite neatly as 2 pints per person per week for the whole country. Okay. So if you've drunk your 2 this week, you're bang on the national average. There we are. And here's a somewhat scary statistic. The world's population is growing very, very fast. We're 7 billion at the moment. Who knows how many we'll have in 50 years' time. And at a conservative estimate, we need to grow more food in the next 50 years than we did in the last 1,000. Some people have even said in the last 10,000. I suppose it depends how much people have eaten in the past. So we've got to grow an enormous amount of food, and none of this is really possible without a lot of research, a lot of careful thought, and a lot of careful planning. But can maths do anything about it? Well, I give lots and lots of talks to schools. I really enjoy going to schools, and you can go into a school and give a great maths talk, and then you say, any questions? And one of the questions I'm often asked is, well, it's all very well what you mathematicians do, but are you really feeding the starving people in Africa? Are you doing anything useful? And my answer to that is very much yes. Okay. I'm going to try to show in this talk that maths is hugely contributing to feeding the people in this planet, and therefore doing an extremely important job. And there's a lovely phrase that you come up with when you're talking with people. We talk about from farm to fork. Okay? From all the way from the start of the food production to the point where it gets to our plate. And here are some of the areas where maths is important, and I've kind of listed them in sort of sequence, going down and then down here. So maths is important in growing food, irrigating food, controlling the pests, harvesting, feeding, freezing, storing, packing, transporting, making, cooking, eating, digesting, and even getting rid of the waste. In case you're wondering what these pictures are, that's some chocolate. That's fairly easy. One of my friends, a lady called Heather Tewksbury, had the most perfect job in the world. What's the most perfect job in the world? She was the chief chocolate mathematician for Cadbury's chocolate. I mean, beat that. You can't beat that. There's an enormous amount of maths in making chocolate. On the right is a picture produced by one of my PhD students. This wiggly thing here is the intestine, and he was studying the way food goes through the intestine and the sort of patterns that it makes, trying to understand how food is digested and therefore to improve certain types of food meant to deliver energy to you. And that was a very nice project that he did. So all of these areas involve huge amounts of maths. I can't cover them all today, but I want to take you through some of them. And this is very much a personal journey for me. I actually do a lot of my research on the maths of food. It's great. One of the big advantages in doing work on food is that if you go to work with a chocolate company, they give you free samples. They really do, and it's great. And I'm going to talk a bit about some of the maths that's involved. Some of it's a little bit heavy duty, and I slightly apologise for that. I'll try and indicate where the heavy duty stuff is. So it involves differential equations, which is a big area of my research, and a lot of optimization as well, and many other things as well. So this is kind of the journey I'm going to take you through, showing how maths is involved in this most vital of things, feeding the starving people and the world, and also feeding everyone else who isn't starving as well. So we're going to have a look at some case studies showing maths in action and bringing you food to the table. I hope you like this. I spent hours of fun producing that picture. One of my friends actually I think it was a guy called Rob Eastaway, took a tin of this and actually did a statistical count to make sure there were the right number of letters and numbers in the tin, just to make sure. Okay, so we're going to start with the production of food. And basically, the food that we have comes from sort of two areas. You can either have a field or orchard or something like that, where you either grow things or animals live in it, or we can catch food in the sea. Okay, so these are where food sort of comes from. And if you drive down a country lane, it's all idyllic and wonderful, and you look at a field, and you don't necessarily realise that a field is actually a highly complex piece of machinery. It's a very, very complex system. A lot of thought and a lot of planning and a lot of science goes into a field. I work a bit with a company, and that company's job is to produce a field simulator. Okay? Some of you may have played with aircraft simulators or train simulators or car simulators. There is such a thing as a field simulator. And this is a package that's offered to farmers, and they can make various decisions about how they're going to use their field, and it will predict from them the sort of yield that they get. So this is a sort of thing that goes into the field simulator, giving advice to farmers on how to plant the right sort of seeds, how to irrigate them, how to control pesticide and fertilizer. And an area I do an awful lot of work in is localized weather prediction. So a forecast of the weather from the Met Office isn't necessarily of much use to a farmer because they need to know what's happening in their field. And so we work on how to get accurate weather forecasts for a very small region using extra information which the farmer can provide us, like rainfall and wind patterns over the last year. So it's absolutely critical to get right. And one of the reasons it's so critical is, well, my aunt is a farmer. My aunt and uncle are farmers. They farm in Canada. And she's on at me all the time, my aunt. She says, well, you know, every year we take all of our savings, everything, and invest it in one seed crop. And if that fails, we've lost everything. So it's really very, very critical to get it right. And a lot of thought has to go into this. Okay, So I'm going to do a little case study to show you how this works. This is a case study, which is a project that I've been recently involved with. Again, sort of feeding the starving people in Africa, or to be more accurate, helping the farmers produce cocoa, which goes on to make chocolate, which goes on to feed my dog. He's not supposed to, but that's what he does. Okay, so I had to caught him at it. He was eating my Toblerone packet this morning. I had to rescue it. Anyway, so here's a sort of scenario, a sort of project that we're involved with. We're working with farmers who can grow either cocoa, so you grow cocoa in pods like this, and one of those will kind of make up a chocolate bar, or another crop, for example, pineapples. Okay. These are two typical food crops in Ghana. And a farmer growing these crops has to make decisions on how much of their money they will invest in growing them. And there are various things that affect this. Both cocoa and pineapples are affected by the weather, but they are affected in different ways. So if you have a hot year, that's good for cocoa. If you have a wet year, that's good for pineapples. Okay, so you have to make decisions based on things like that. They cost different amounts, and you get a different amount when you sell them. So the question is, how much of each do you grow? How much of each do you grow? So my next slide is a mathematical one. I make no apologies for this, there's maths in the title, but to show you the sort of way we think about these things. So this is the sort of problem that the farmer has. How do we formulate it mathematically? So we formulate it mathematically as a thing called a linear optimization problem, in which we say that in 1 year the farmer might grow an amount C of cocoa and amount P of pineapples. So the more cocoa seed you buy, the more it costs. The more pineapple seed you buy, the more that costs. And the total cost to the farmer is proportional to the amount of cocoa, so that's A times cocoa plus B times pineapple plus a fixed cost of labour, which you've got to pay whatever you buy. So that's your cost. Again, in a farm, you've got limited amount of space. The cocoa trees take up so much space. The pineapples take up another amount of space. So that's the amount of space that you take up. And then the profit that you make, well, obviously, the more cocoa you sell, the more profit. The more pineapples you sell, the more profit. And that's the profit that you make. So this here is the sort of what we call the constraints. This is what you want to maximize. And the farmer's task at the beginning of the season, when they try to choose what to plant, is to say, how can I choose C, that's the amount of cocoa I plant, and P, the amount of pineapples I plant, to maximize my profit. Okay, they want to maximize their profit, but they have two constraints. One constraint is that the cost here must be less than some maximum, which is their, whatever they've got, their capital investment, what my aunt has to invest. And secondly, there's obviously a limited amount of space on the farm, so they have to do that. So there we have it. There's the mathematical problem, which looks kind of stark, but that problem is directly related to cocoa and pineapples, and is therefore, by solving it, we can help the farmers in Africa. So it's a very important problem to solve. And this is a problem which involves just two crops, cocoa and pineapples, but you could extend this quite happily to have any number of crops and other constraints as well. So this is where kind of a mathematician thinks. And what's nice about this problem is that you can solve it. These problems were sort of looked at just after the war, when the subject to operational research was really getting going, and people were asking questions of how to maximize profit, particularly in a factory, where you have various constraints about the way you make things. And this problem was solved by a guy called Danzig. And he came up with a thing called the simplex algorithm. Now, if I was to be asked what were the great, mathematical achievements of the 20th century, if you ask a pure mathematician, they might say, solving Fermat's last theorem or something like that. But as far as I'm concerned, the development of the simplex algorithm was one of the key breakthroughs of 20th century mathematics, being able to solve these sort of optimization problems. I've talked about cocoa and pineapples, which is quite a simple problem, but if you want to optimize, for example, the way that you have aeroplanes flying around the world and where you put cabin crew in them, so that's thousands of variables, you actually end up solving very, very similar mathematical problem, and this guy, Danzig, worked out how to solve it. And basically his idea was that you plot these constraints here, that's a straight line, and that's a straight line. If you plot them, you get a region, which I've, like this, that's one of them, that's the other one, you get a region which I shaded in, and you look for the corners of that region, and the corners, you go through each of the corners and you work out the profit, and you find the one which gives you the biggest profit, which in that case is this one, and that's your optimal solution. Okay. And the same idea works beautifully, I say, for air traffic control, for factories, and for many, many other problems. This simple thing, the simplex algorithm, as I say, is one of the key contributions that mathematics makes to the world's economy. One of the mysteries about it is it works extremely well, and it works a lot better than it essentially should. No one quite knows why it works as well as it does, but anyway, that's God's little joke for us. So that's a big area that mathematics is helping farmers essentially in allocating the resource. But just to show you sort of my own work on this, as I said, one of the other factors that influences the growth of crops is the weather. And here are two plots which I've been working with recently to do with Ghana, where this is the maximum annual temperature in orange. The orange here is the mean annual temperature, and the blue is the yield for the crops. And what's very nice from this is that we can see that there's actually quite a close correlation between the rise in the crops and the rise in the annual temperature. This is global warming, but in this case working to our advantage, or at least the advantage of the cocoa producers. And then the variations on top of that are very closely linked to the maximum annual temperature. So the point is, if we can get a good handle on what the climate is doing and the weather is doing, that allows us to make good predictions for the farmers. Next year, I'll be talking a lot more about climate and global warming and so on, and we'll see some of the negative effects. But this here is actually a positive effect. There are other factors as well. One of the more interesting things about cocoa production is that there are actually 2 harvests per year rather than 1, and that's because there are essentially 2 rainy periods in Ghana during the year rather than 1. Okay, so that's how we do farms, and similar techniques are used to advise farmers in the UK as well. But mathematics is also used in the other source of food, which is the sea. So if I was giving this talk in Spain or in Japan, the majority of the food in those countries, particularly Japan, comes from the sea. And mathematics is very much used to help predict and understand the way that fishing populations operate, and to guide fishing fleets into sustainable ways of harvesting a population. So before Brexit, this was done at a European level. I'm not sure whether it will continue that after Brexit, but certainly the EU was using mathematical models to try to understand fish populations around the shores of Europe, and that was then used to regulate the way the fishing industry was harvesting the different types of fish. And this is the sort of equation they use. This is what we had in the last few transparencies was mathematics of optimization. This is more my sort of field, which is the mathematics of differential equations. And this is the sort of equation that's written down. It's actually quite a long history. A guy called Malthus in the 18th century started writing down equations a bit like this in order to try to predict the way that human populations would grow, in particular how they would grow if there were limited resources. So human populations, if you've got unlimited resources, grow exponentially fast, but after a while that growth slows down as they start using up the resources. So this is a sort of equation the fisheries people will use. If you go onto that source of all wisdom, Wikipedia, it'll take you through various other models, and in fact the article's quite good. And this is saying here that the growth rate in the amount of fish, df by dt, that's the rate at which fish grows, is given by A, which is a kind of essentially reproductive rate of the fish, times the amount of fish. And this term here gives you the effect of limited resources, and this term here is the effect of fishing. So B of t is the harvesting rate of the fish. And so that equation, or equations very like it, are in use constantly by fishing industries to moderate and predict how fish grows. This is a single fish species. In practice, you would have a number of these different equations to count for the different types of species, and you would also have different terms here for the different growth rates and harvesting of those things. So that's how food is essentially produced. Okay, so that's the first thing that we want to talk about. So once you've produced food, the next thing you have to do is to store it. One of the big problems about food, particularly transporting it, is that food has a very short lifetime. Okay, food can go off very quickly. There's some ridiculous, horrible estimate that about a third of the food that we produce in the world is thrown away. And the reason it's thrown away is you can't get it to where it needs to be got to in time for people to eat it. It goes off. Think of that, 1/3 is thrown away. It's a staggering amount. And mathematics can very much help here, and it essentially goes back to that great mathematician, Lord Kelvin. So Lord Kelvin did many great things. He designed the cables that go under the Atlantic, linking England to America. He designed the basic design of the ship's compass. But perhaps his greatest achievement was he came up with the laws of thermodynamics that we use all the time to study engines and heat flow, and in my own work I use them to study the weather. So Kelvin wrote all these things down, and a good understanding of thermodynamics led absolutely directly to the use of refrigeration to store food. So before this, food was basically stored either by salting it, which reduced a lot of the nutritional content, or by drying it, which had the same sort of effect, or by packing it with ice. The problem with that is you've got to get the ice from somewhere, and there's only so many icebergs, as it were. So Kelvin and his work led directly to the use of refrigeration. And if you think about it, refrigeration is everything. Pretty well all of our food at some point gets stored in some sort of refrigeration system. Another scary slide coming up. You'll get these occasional scary ones, and I will warn you. Oh, that's not the scary slide. Well, it's pretty scary in a way. So here's the question: how do we safely freeze food and keep it frozen? Okay, if you freeze food too fast, you'll kill it. You won't kill it; it's dead already. But you'll make it uneatable. You'll destroy it. If you freeze food too slowly, then it's uneatable. It will go off. So you've got to get it frozen at the right sort of rate. Okay, now the scary slide. Here we are. So this is one of my favourite equations. That's the basic equation for all frozen food. For all frozen food. They don't tell you this on the can when you buy your tins as well, but that's it. And this equation here, on the right, T is the temperature of the food. This horrible thing here tells you how heat spreads out. Okay, so typically when you freeze food, it spreads out by essentially a process of conduction. On the left, you've got a thing called the enthalpy. What's the enthalpy? The enthalpy is basically the energy of the food. The energy of the food. And the energy is a combination of the thermal energy, that's the temperature times the heat capacity, plus the energy you require to essentially the latent energy tied up with the freezing process. And some foods have a vapor or gaseous process as well, and that's called the energy. So it's basically the enthalpy, and it says that the change of the enthalpy with time is proportional to the change of the temperature with space. So that's an amazing equation. It's an extension of equation which was developed in the 18th century by a genius mathematician called Fourier. And this little equation here is used all the time in the food industry to understand how things are frozen. Or conversely, if you want to thaw something out and then use it, how to thaw something out. So a lot of my life has been spent trying to find good and accurate ways of solving this. And part of it involves this equation here. I won't go into detail, but when you freeze something, I don't know if you've ever frozen anything, you should do it sometime. Typically, you have an unfrozen region and a frozen region, and you get what we call a Stefan problem, where the freezing front moves across the food and the food progressively gets more and more frozen. And studying that is called a Stefan problem. We use exactly the same equation to study the growth of ice in the Arctic or the growth of ice in the Antarctic and all sorts of things like that. It's the same equation, same maths, different problem. And these are the sort of things that we have to solve. Now, just to give you an indication of how important this is, you are probably very used at home to storing food in a fridge, okay? And there's a little light that comes on and stuff like that. That's how food is stored if you are a supermarket or something. They store it in warehouses which are the size of football pitches. Okay, huge warehouses are used to store food, and these have to be extremely carefully regulated for their temperature, and all sorts of guidelines have to be put into place to make sure that when you use them, the food stays cool. And one problem that came, well, not my way, but the way of a colleague of mine, was that some people in a warehouse was an absolute panic. And the reason they were in a panic is that some twit had opened the door to the warehouse and had forgotten to shut it. Okay? And there's supposed to be all sorts of things in place to make sure you shut the doors, but they'd opened it and hadn't shut it. And the door had been open for longer than the time it was supposed to be open. And the question was, did that mean that the food in the warehouse was now unsafe? Okay. So we had to do a calculation to see the effect of holding that door open for too long, given the temperature outside and various other things. And that calculation was able to show that for the length of time the door was open, the food wouldn't have got corrupted. So in other words, the food was safe, and so they were able, by that simple process, to save an entire warehouse of food. You know, huge amounts of food, which then could obviously go on to to be used to feed people. So that's a simple bit of maths, saving millions of pounds, but also potentially saving lots of people's lives. So freezing food is extremely important. We've got to get it right, because if you get it wrong, then the food goes off, and that could possibly lead to people dying, which is not what you want. Okay, so let's get on to a more kind of cheerful aspect of food. Well, not food, beer. Okay, so we all like beer. Well, I hope we all like beer. I certainly like beer. And mathematics is actually significantly important in beer. I'll tell a story in a minute to show particularly why it's important. But one of the nicer aspects of beer is that beers have foam on the top. Okay, so the foam acts both to enhance the look of the beer and to a certain extent enhance the taste of the beer, because it affects the way the tongue interacts with the beer. Beer companies actually invest quite a lot of money in kind of the mathematical aspects of beer, whether it's from the fermentation process to the storage, to the sedimentation, or to the foam. I once, when I was a PhD student, attended a seminar in Oxford where I was doing my PhD, and the seminar was entitled The Maths of Beer. It was the best attended seminar I ever went to, particularly as it had practical sessions. In fact, we all had to drink 3 pints, and we're pretty good at the end of that. Very, very good seminar indeed. Anyway, so what's a foam? So if you have a beer like lager, then the foam is basically made up of carbon dioxide. So when you make beer, the fermentation process releases carbon dioxide. The carbon dioxide nucleates around small particles within the beer, and the bubbles rise through the beer. You can't quite see because the fingers are in the way, and eventually forms a foam at the top. And what the foam is bubbles of carbon dioxide separated by the liquid of the beer through surface tension. And lots of people have studied foam. There's a very nice kind of mechanism for producing a foam, which is called Oswald ripening. Oswald ripening. And the way Oswald ripening works is that it says that the way bubbles change depends upon their curvature. So a small bubble is very curvature, a lot of curvature in a small bubble, and that tends to mean it shrinks, whereas bigger bubbles have smaller curvature and they don't shrink so quickly. And what it means is that the small bubbles get eaten up by the larger bubbles. Okay, it's what it says in the Bible. To those that have shall be given more, but those that have not, what they have shall be taken away. So that's obviously definite reference to bubbles in beer. Okay, so the beer builds up, so you get these kind of large bubbles forming by this Oswald ripening, and they make a lovely pattern. And that pattern was studied and essentially classified by this guy here, von Neumann, who is one of my big heroes. An incredible polymath, if you've never come across him. He started life as a very pure mathematician, studying things called Banach spaces. He then went on to develop game theory. He was, to all intents and purposes, one of the key inventors of the modern computer, and he did a lot of work on fluid dynamics and other problems as well. Incredible polymath there. He is standing behind one of the computers that he invented. And he studied foam on beer, well, foams in general, and worked out the sort of patterns that you make. So next time you drink a glass of beer, have a look at the foam and enjoy the pattern. Now, there are different types of beer. There's lager, like this, but another type of beer, or to be correct, stout, is Guinness. And here's a pint of Guinness. And if you look, Guinness and lager, that's got a small, kind of fairly weak foam on the top. And look at that. That's a glorious foam up there. Guinness have invested a lot of thought into how to make that foam really good. And there's a crucial difference between the foam in Guinness and the foam in lager, and that is that the foam in a pint of Guinness isn't made up by by carbon dioxide. It is made up by nitrogen. Now, nitrogen diffuses much more slowly, and the bubbles of nitrogen are much smaller, and so you get much smaller bubbles, which are much more stable. And the combination of the smaller bubble and the stability means that you get these much more longer-lasting foams. So Guinness, has put a lot of research into how to do that. Now, if you go to a pub and you order a pint of Guinness, in fact, when I last gave a talk related to maths of food and drink, I actually gave it in a pub so we could do some practical work as well, which was fun. In a pub, the Guinness it comes out of the barrel, but at the same time there's a pipe coming up from another barrel which has nitrogen in it, and that introduces the nitrogen at the point of serving, and that's how you get the foam here. And for many years, if you bought Guinness in a can, you didn't have a foam, but then in the 1980s, I think it was, Guinness introduced a thing they call a widget. There it is, which is a little ball full of nitrogen. And when you have a can with a widget in it and you open it up, the widget releases the nitrogen, and so you can get a creamy foam out of a can. It was a great advance. Now, you might think, wow, this is all very good, you know, what's the maths in that? Well, I don't want to say that I've studied this, because other much greater men than I, or women than I, have studied this in depth, and this is one of my favourite papers. It's got the best title of any paper I've ever read, The Initiation of Guinness. The Initiation of Guinness, which was written by, as far as I can tell, the entire maths department of the University of Limerick. Okay, who says mathematicians can't have fun? So there we are, the entire, pretty well, I think everyone has got in on this one, plus a few industry representatives as well that have clearly come over from Guinness and various other places. So there we are. If you ever thought maths was dull, go to Ireland and go to... I should say, in case you think that I've kind of completely rubbished this group, they, after writing this wonderful paper, wrote an equally wonderful paper on the maths of coffee. Okay, so the Maxi group in Ireland, a terrific group doing industrial mathematics. Okay, so let's keep on the subject of Guinness, and I want to tell you a story about how a group of statisticians in reality could not organise a piss-up in a brewery. So this is absolutely true. And it's all centred around this fantastic guy here, who is called Gossett. Now, Guinness absolutely knew that maths was important for making Guinness. So we've seen how maths is important in the initiation of foam, but they were particularly interested in Dublin in the early part of the 20th century in how to control the quality of their product. In particular, to check that all the batches of Guinness that they were producing had consistent high quality. And they had the enlightened policy of recruiting very, very good statisticians, particularly from the universities, to come and work for them. And one of the guys they recruited was this guy called Gossett, who kind of alternated his time between Guinness and UCL, University College London. Gossett, they're not quite sure whether when he was either at Guinness or UCL, but it didn't really matter because it was used at Guinness, determined a statistical test which basically worked out whether two batches were a similar quality, or could tell whether two batches had different quality from each other. Very, very important test. And he was very pleased with this test, and so he wanted to publish it. But Guinness didn't want anyone to know what he was doing for Guinness, and so they wouldn't let him publish it under his own name. Okay, so he had to invent a name. So he invented the name of Student, and in 1908 published the test that he came up with under the name of Student, and ever since then it's been called Student's t-test. If you do A-level mathematics or university-level mathematics or do any statistics at all, you will be using Student's t-test. It's one of the most important statistical tests there is, and it is widely used both in the food industry and many other industries for comparing batches of things to make sure that they all have consistent quality. And it all goes back to this marvellous guy here. So where's the story why the statisticians couldn't organise a piss-up in a brewery? It goes back to the British Science Association. Well, in 2005, when this incident occurred, this was called the British Association for the Advancement of Science. And they decided to hold their annual science meeting, the British Association meeting, in Dublin. Okay, in Dublin. So in 2005, the BA meeting was held in Dublin. It gets held all over the place, and I've often gone to it, and in fact, due to the effect of working with a previous Gresham professor, I even have had to dress up in fancy dress when I go there, but that's another story. Anyway, this is Trinity College Dublin, and the British Science Festival was there. And I, at the time, was chairing the committee to organise the maths events at the festival. And our committee came up with the idea that given that the t-test came from Dublin, Guinness in Dublin, it would be a really good idea if the Royal Statistical Society could maybe organise a reception in the Guinness brewery, and we'd hang this reception around the fact that it was the t-test, so we could celebrate mathematics and also go to a reception in the brewery. And so the Royal Statistical Society was given this task, and off they went. And sometime later, I got this letter back from the organiser of their committee to say that due to operational problems, they weren't able to do the reception that we asked in Guinness to do the t-test. And we looked around at each other and realised that the RSS had just admitted that they could not organise a piss-up in a brewery. I should explain, there's a little bit of a tension between applied mathematicians and statisticians, and so we enjoyed ourselves on that. Okay, so let's move on. I want to talk about eggs now. So another source of food, very important source of food, is chicken eggs, and indeed chickens. Okay, so a hugely important food stuff. Eggs are often, if you want to produce more chickens, you incubate them. You incubate eggs. So I could tell you a little bit about that. No, it's not. I'm going to tell you a bit about that. So when you incubate eggs, it's simply not economic to get a chicken laying an egg and incubating it. Typically what you do is you take the eggs and you put them in an incubator where you control the temperature and the humidity, and you turn the eggs as well in order to produce healthy animals. Now, I could tell you about chickens, but I want to slightly divert from my theme of maths and food to tell you about a project that I was involved with, which I really enjoyed, which is kind of related, which came from Bristol Zoo. And Bristol Zoo had these things, lots of penguins, and they didn't want to eat the penguins. That wouldn't be right. They wanted to produce more penguins. And the way they wanted to produce their penguins was to take the eggs that the penguin lays and incubate them in the same way that you would incubate a chicken egg. So in the incubator, they were controlling the temperature and the humidity. They were constantly rolling them. But they found that the eggs were dying. So they were only about 10% survival rate for the eggs. So the problem they got us mathematicians involved with was to help them design a better, particularly a better turning strategy to allow the eggs to increase the survival rate for the penguin eggs. So that's the problem that we were given. And the basic statistic that we were given is if it's a mother penguin, or in fact, penguins are very democratic. The fathers often sit on the eggs as well. They will typically turn their eggs once every 20 minutes. So they wanted us to come up with this kind of theory for what's going on and then use that to improve their incubators. There's a typical egg. You've got the shell. You've got the albumen, which is the white of the egg. Inside that, you've got the yellow, which is the yolk. And on the top of the yolk, you have a thing called the blastoderm, which is the bit that eventually develops into the chicken, or in this case, the penguin. And the mother or the father would typically sit on the egg. The reason for sitting on the egg is essentially to keep it warm. As I say, they turn the eggs every 20 minutes or so. So we were doing this work for Bristol Zoo, and they had the theory that the reason that the mothers were turning the eggs every 20 minutes was to make sure that the temperature in the egg was uniform. So you'd sit on the egg, heat up a bit, then turn the egg, heat that bit up, and so on, and keep it all warm that way. We had a couple of other theories. One was that the egg was turned in order to disperse the nutrients within it, and another one was that you had to remove the waste products. And again, all this applies to chicken eggs as well as to penguin eggs. So off we did do some math. What was the equation? Well, actually, you write down the same equation that you write down for freezing food. You don't want to freeze an egg, obviously, and so the equation is slightly simpler. This thing here is called the heat equation. Instead of enthalpy, the energy is just in terms of heat and how it spreads out. So that is the basic equation for the heat transfer within an egg. There's the mother sitting on the top, and there are various numbers here which you can find. That's the diffusivity, and the radius of an egg is 2 centimetres. So you can take that equation and say this equation is possibly the most important equation when it comes to working with food. If you're an undergraduate, you'll meet that probably in your second year and learn how to solve it. So there are 3 mothers. There's some eggs. And this is the temperature. Brown is hot, blue is cold. That's after 10 seconds. That's after 2 minutes. And after 20 minutes, what we discovered was that the whole of the egg was nice and hot. What did that tell us? This simple calculation says if a mother sits on the egg, after 20 minutes it's nice and hot, the mother doesn't need to rotate the egg to keep it warm because it's warm already. So the mother is turning the egg for a different reason. The Bristol Zoo was turning the eggs to keep them warm, and that was entirely the wrong thing to do. You actually needed to find a different process for that. So this little simple calculation here showed us what they were doing was wrong. It led us into the correct answer, which was to find a turning strategy to distribute nutrients, which you can do using rather scarier maths. And we managed to increase the survival rate from 10% to 90% by doing that. So we managed to save the penguins. Who says maths isn't fun? Okay, so let's move on to the potato, which I put up earlier, and I'm sure you are all thinking about in terms of lunch. Here's a sort of story which goes back to the Second World War and the University of Birmingham. I'm very pleased to see that the new person in charge of the admissions desk as you came in was a Birmingham graduate. One of the things that happened in Birmingham during the war was 2 guys, Randall and Boot, working in the physics department under Oliphant, invented a thing called the cavity magnetron. There it is. This is their invention. The cavity magnetron is a device for producing radar waves. So during the war, there was a great need to produce high-energy radar at wavelengths of a few centimetres. The technology at the time was using things called klystrons, which were simply not producing the amount of power needed. And this thing here, which uses a combination of high electric fields and magnets, spins electrons round, and spinning them round produces high-energy radar waves. And this simple device was a war-winning thing. It produced the radar that was used in the aircraft. It produced the radar that was used against the U-boats. And it was so important that it was taken in a secret box to America to be produced in mass quantities as part of the kind of encouraging America into the war strategy that was going on at the time. So this is the cavity magnetron. One of the guys in America responsible for developing it was this guy here called Percy Spencer. And the story goes that he was producing high-power radio waves through a cavity magnetron and realized that the candy in his pocket was getting very warm, in fact melting, and he deduced correctly that it was because the microwaves coming out of this were heating it up. And so it was a short step from that to inventing the microwave cooker. So here's the inventor of the microwave cooker, and most of us, I think, use a microwave cooker to cook our food. Okay, well, certainly students do, and certainly I do when my wife's away. Okay, so even when my wife's in. So microwave cookers are very, very important, and so I want to tell you just a few shortly about how microwave cookers sort of work and a bit of the maths behind them. So there's a microwave cooker. There's a tray, typical food in there. This thing here is called the cavity, and sitting up here, you can't see it, it's somewhere in there, is the cavity magnetron, the same cavity magnetron that was invented at Birmingham. Pretty well the same design, has worked so well they haven't had to change it very much. Here's a potato, and one of the questions that we thought quite hard about was how safe is a microwave cooker? And here's a question. Do microwaves cook from the outside in, or from the inside out, or something else? Okay. Microwave cookers are often advertised as cooking from the inside out, as opposed to a conventional oven which cooks from the outside in. In practice, it's somewhere else. Something else is that if you put a food stuff in a microwave cooker, it goes on a turntable. The reason it goes around in the turntable is that electric fields in a microwave cooker have hot spots and cold spots, and if the food sits in a cold spot, it won't get cooked, so the turntable moves it round. More modern ovens have a thing called a mode stirrer, which is basically a metal fan in front of the microwave cavity, and that it disperses the food and breaks up the cold and hot spots. Here's a picture that we took of foodstuff in a stirred oven with an imaging camera. So with that fan, and that was quite satisfactory. That food's all cooking kind of nicely. This is a slightly scarier picture of a foodstuff in a turntable oven where the turntable isn't doing its job, and you've got a cold spot in the middle. That food would actually be quite dangerous. Okay. So this is a cross-section of the food after you've heated it and cut it through, and you can see it's very hot on the outside and cold on the inside. Microwaves do not cook from the inside outwards, nor do they cook from the outside inwards. They cook from about here outwards in both directions. Is a rough explanation of what's going on. So let's have a look at the maths. So the maths is you have a cavity, and in the cavity you have scary equations, Maxwell's equations, which describe the electric field. The electric field gets into the potato in this case and starts to heat it up. So the microwaves, here's the potato, this is the boundary of the potato, come in, hit the boundary of the potato, heat it up. And so our question was, how does that heating process work? And here's the scary equation. So you might recognize this one here. That's exactly the same equation that we had for the frozen food, the entropy equation. But we can stick in a thing here, which is called P, which is the power. And the power tells you how the microwaves are heating it up. It's proportional to E squared, where AE is the field, the electric field from microwaves. And so basically you've got energy produced here, conducted away, and that heats up the thing. What's the crucial equation here? The crucial equation here is actually this one. Ignore that one. And that says that if you go into the food, and this is in special units which are kind of normalized so that the food is 1 unit in length, the field drops off e to the minus 12y. Now, if you're not familiar with this, this is the exponential function, and that tells you that the field actually drops off very rapidly as you go inside the microwave oven. This is important. The reason it's important is that when you heat up a foodstuff in a microwave oven, the field decays quickly as you go into the food, and if you go more than about a centimetre into the food, it's actually going to be cold. It's actually going to be cold. And this equation here you can solve, and here are some pictures of a typical foodstuff, in this case mashed potato, which we have simulated using those equations. And the red is hot and the blue is cold. So the outside of the food gets quite hot. Here we are, the food is hot on the outside, but the inside stays cold, and it stays cold for quite a long time. And this is actually quite a worrying thing, and we were giving advice to the microwave cooking people and also hospitals which use these. If you ever buy a microwave meal and you look on the packet, it says something. It says heat for 5 minutes and then wait, or heat for 5 minutes and then stir. And the reason for that is the microwaves won't heat the food properly, but if you allow it to stir it or wait, it will then heat up by other means, and then you'll get the temperature right. But do not rely on a microwave to get your food uniformly hot, because it can't do it. And that's a useful thing that mathematics can tell, and hopefully save some lives in the process. I'll whiz through that one because I haven't got time, and I shall finish with the transport and delivery issue, which is the one I started with, saying it doesn't matter how much food you produce, unless you can get it out there and get it out at the right time, you're going to lose about a third of it. And so perhaps almost the most important application of mathematics in the process of food is to design good transport mechanisms and good delivery mechanisms. Here's an interesting picture. Here is a world, and the countries are plotted, and the area of the country plotted is proportional to the amount of fast food that's eaten. Okay, so America's doing well, and England's doing horribly well. There we are. And so you can see Africa's got almost nothing. How important it is to get food fast to different places. Again, this is an area which has been studied very heavily, and nowadays delivery strategies are worked out by solving a thing called the travelling salesman problem, which was felt to be insoluble until quite recently, and is now being solved using advanced things called stochastic algorithms. So the travelling salesman problem tries to work out routes which get you around many destinations as quickly as possible. And these algorithms are really being used very, very heavily now to solve a lot of the food delivery problems that are so important to get food to us at the right time. So I'm nearly up to time, and I want to finish with a very, very bad joke, which you have to be a mathematician to understand or get. So I apologise, but not very much. But I will just finish with, to show how stupid mathematicians are. So here goes the joke. If you don't find it funny, it doesn't matter. It's actually not very funny anyway. But three mathematicians go into a pub, and the bartender says to them, "Does anyone want a pint of lager?" Does anyone want a pint of lager? So the first mathematician thinks very hard and says, "I don't know." And the second mathematician thinks very hard and says, "I don't know." And the third mathematician thinks very hard and says, "No." So then the bartender says, "OK, does everyone want a pint of bitter then?" And the first mathematician thinks very hard and says, "I don't know." And the second mathematician thinks very hard and says, "I don't know." And the third mathematician thinks very hard. Any mathematicians in the audience, what does they say? Yes. And so they all have a pint of bitter. Now, I'll leave you to ponder that. It's in the notes. Go away and think about it. And whilst you think about it, have a nice lunch, enjoy some food, and perhaps think about how maths does actually feed the starving people in the world. Thank you very much.